Welcome to example number 2. In this question, we're asked to find the weight of the Hubble telescope and what it would weigh if it was on the surface of the Earth, and then also what would be its weight while it's in orbit around the Earth at a distance of 598 kilometers from the Earth's surface. Now, the weight of an object is the total gravitational force exerted on the object by all other objects in the universe. Now, when the object is near the surface of the Earth or on the surface of the Earth, when we can neglect the other gravitational forces and really just only consider the force of gravity between, say, the telescope and the Earth, because that would be the strongest force. So we'll neglect all the other forces from other masses nearby. The weight of an object can be calculated in two ways. The simple way of calculating the weight would be just simply taking the mass of the object, which is 11,600 kilograms, and multiplied by the acceleration due to gravity at that location, which on the surface of the Earth is 9.8 meters per second squared. And we can do that in part A because it's resting on the Earth. So if we were to calculate the weight of the Hubble telescope on the surface of the Earth, it would be 11,600 kilograms multiplied by the acceleration due to gravity on the surface of the Earth, which is 9.8 meters per second squared. And that will give you an answer of 1.14 times 10 to the power of 5 newtons. Now, there is another way of solving for the gravitational force, and that would be using Newton's universal gravitational law, which states that the gravitational force is directly proportional to the product of the masses, so we could call this m1 and this m2, and then divide it by the distance between the two masses, so the center of this mass and the center of that mass, and we'll call that r squared. The formula works out to be Fg, which is the force of gravity, equals g, it's a constant called the universal gravitation constant, multiplied by the mass of the first object, let's say the Earth, multiplied by the mass of the second object, which would be the Hubble telescope, divided by the distance between the two objects, which we'll call r squared. So we can modify this equation a little bit, maybe just call this m instead for the mass of the Hubble telescope. And then we'll replace m2 with the mass of the Earth, and we'll replace r with the radius of the Earth. Okay, so now let's substitute in our gravitational constant, the universal gravitation constant, not to be mistaken with the little g. This is the acceleration due to gravity, and this is the universal gravitational constant. It's 6.67 times 10 to the power of negative 11 in Newton meters squared over kilograms squared. Then multiplied by the mass of the Hubble telescope, which is 11,600 kilograms, multiplied by the mass of the Earth, which you would have to look up, and that's about 5.972 times 10 to the power 24 kilograms, and then all divided by the radius of the Earth, which is given over here, of 6.38 times 10 to the power 6 meters, and that quantity is squared on the bottom. And you will get an answer of 1.14 times 10 to the power of 5 newtons. It won't be precisely the same as that. If you use all the digits here and here, you might not get the same thing. You have to remember that we're assuming that the Earth is basically a nice spherical, symmetric object where the radius is always constant, and it isn't. And so there are some assumptions, but you get pretty close to that answer here. Okay, so moving on to part B, you can see the two ways that we could have done part A. Part B, we're now moving the telescope here at an elevation of 598 kilometers above the surface of the Earth. So you have to realize that the acceleration due to gravity is no longer 9.8, and we don't know what it is here. Now, I suppose we can calculate that if you look down below in the next section. But let's calculate the weight of the Hubble telescope now utilizing the second method, which obviously was longer to solve part A that way, but you can use that now more precisely in part B. So the force of gravity, we'll just call that prime, the new force of gravity, would be g times the mass of the telescope times the mass of the Earth, divided by, now the telescope is no longer at a distance of the radius of Earth, but it's at the radius of the Earth plus that altitude of 598 kilometers. And that quantity is being squared. So now let's go ahead and substitute in our values. And there you go. There's all the substitute values. Notice I had to change the 598 kilometers to 598,000 meters, right? We want to make sure our units all cancel out. The meter squared here will cancel out with the meter squared down below. And go ahead and compute that on your calculator. So then our force of gravity, the new one at that location, is now 9.50 times 10 to the power of 4 newtons. You can see it's less than what it was on the surface of the Earth. Right? And that's because the acceleration due to gravity is getting, there's less pull because that distance has gotten larger. So as you move further and further away from the center of the Earth, your force of gravity gets less and less. And that's it for this example.